Good evening to everyone wherever they are attending this webinar. I am Ali Rahman, hosting Pavement webinar series, an initiative we just recently launched at Southwest Jiaotong University to enrich our academic environment by inviting distinguished and international experts, researchers, and scholars across various domains of pavement engineering and materials to share their insights and expertise as a speaker in this webinar series. In fact, the core objective of these initiatives is to expose our students, researchers, and faculty alike to the forefront of research and the latest advancement in pavement engineering, pavement structure, pavement materials through this pavement webinar series. And today is the seventh episode of this webinar series. And the topic of today's presentation and today's webinar is, can the uniaxial thermal stress and strain test helping designing thermal crack resistance asphalt mixtures? And our today speaker is Professor Elie Hajj from University of Nevada, Reno. And Dr. Hajj is currently a professor in the Civil and Environmental Engineering Department and an associate director of the Western Regional Superpave Center at University of Nevada, Reno. He has over 18 years of experience in academia and industry with an emphasis on sustainability of pavement systems, dynamic response of pavement structures, and full-scale testing of pavement systems. Dr. Hajj, co-author over 120 publications in journal, national, and international conferences and technical reports. He made more than 150 presentations in professional meetings, conferences, seminars, and workshops. He also served as a principal investigator on multiple projects for FHWA, FAA, state DOTs, local governments, private industry, and so on. He's currently a member of Association of Asphalt Paving Technologies, a founding member of Academy of Pavement Science and Engineering, a member of American Society of Civil Engineers and Transportation Research Board. In the meanwhile, he serves as a member of the board of directors and as a vice chair of International Society for Asphalt Pavements. And also, he is currently an associate editor for the International Journal of Pavement Engineering. So thank you so much, Professor Hajj, for accepting my invitation. It's a privilege to have you in this webinar series, and thank you so much for your contribution. Before I give the floor to Professor Hajj, for those of you, for our audience who are attending this webinar, after the presentation, we will have a Q&A session. So whether during presentation, you can type your question in the chat box, and I will read the question after the presentation, and hopefully Professor Hajj will reply. Or you can directly after presentation raise your hand, turn on your mic, and ask directly your question from Professor Hajj. With that, I will stop now my sharing and give the floor to Professor Hajj. Thank you so much, Professor Hajj. Thank you.
Well, thank you very much, Ali, for the introduction. It's a pleasure for me to be here with you. It is the afternoon for me. It is, what is it now? 9 after 6 p.m. And I believe it's the morning, your time. When Ali asked me if I can do these presentations, obviously I was excited to do that. My only question was, what time should it be? Because given the time difference and everything. But I'm glad that we were able to find a good time that you guys can attend. My presentation today, I'm going to talk about a little bit about the uniaxial thermal stress and strain test. and specifically in the context of thermal cracking of asphalt mixtures. So I'm gonna, maybe some of you may not be familiar with what we call the UTSST, as it stands for the Uniaxial Thermal Stress and Strain Test, but I'm gonna give you a little bit of backgrounds. But before I get into my technical talk, I wanna basically introduce a little bit for you where I am right now. So if you are familiar with the United States map that you're seeing here in front of you, so basically I am located in Nevada, and specifically in Reno, Nevada. And this is basically where I'm trying to get my laser over here. There you go. And this is the state of Nevada. I don't see your hands, but usually I ask the questions, how many of you been to Las Vegas? And Las Vegas is the biggest city in Nevada. Is actually the largest city of the states. But Vegas is on the south east part. We are here on the northwestern part. So while the states in general is known for being a desert environment, Reno is actually closer to the border, and it's a higher elevation. The border, and I mean here more closer to California. It's a higher elevation. It's a beautiful campus. This is a picture of our campus, and we do have actually 4 seasons in Reno, including the spring, the summer, the winter, and the fall and the winter, and a beautiful actually winter where we get snow. And we are only about 40 minutes from Lake Tahoe, one of the cleanest lake in the world, and where you get to do ski or snowboarding while basically observing the beauty of the nature and the lake. With that being said, I'm part of the Civil and Environmental Engineering Department at the university, and we do have a program that's called the Pavement Engineering and Science Program. The director of the program is Professor Peter Savali, and then I have my colleague Adam Hand and myself. So we have 3 faculties specialized in pavement engineering and science. We do have a research scientist, a PhD, and then also we have about 15 to 20 graduate students and about 3 to 5 undergraduate students. That's typically what's our program. That QR code that allow you to take you directly into our websites. Now, what is our faculty expertise? So while all 3 of us overlap, but we do have very specific niche, if you want. We do a lot of work and expertise in advanced material characterization and sustainable pavement systems, especially when it comes to recycling of asphalt pavements. Dr. Hand brings tons of experience in quality management, whether in materials or construction, and project procurement and deliveries. I do a lot of works as well in pavement responses to dynamic transient loads, and also we do a lot of works in pavement preservation and management systems. And that's why it's basically, we always talk about a pavement system, from the material to the design of the material, to the pavement design, to the pavement management, to pavement preservations, and basically recycling and start all over again. We cover that not only in our research, but also we are within our graduate courses. We are the only university that I'm aware of that we offer 8 graduate courses related to pavement engineering and science. Everything you think about it, it's in our courses. And we have a state-of-the-art labs for aggregate, soils, asphalt binder, asphalt mixtures, Portland cement and Portland cement concretes, as well as we have a full-scale pavement testing facility. The box that you see over here is 11 feet by 11 feet by 7 feet deep, which we can fully instrument and apply dynamic loading at the surface. And we do produce our asphalt mixtures on site. We have a half-a-ton asphalt mix equipment that allows to do cold mix or hot mix. And I would like to say we are the first lab, university lab, to be ASTO accredited in the United States. We were the first lab to get the accreditations back in late 1990s, early 2000, and we still maintain that. It's over 25 years now, and we still maintain our ASTO accreditations. I want to also mention quickly that we do have, where we offer graduate research assistantships to all of our students. If you recall, I said we have about 15 graduate students per semester. They're all fully funded. And what I mean by this, we pay their tuition, we pay their health insurance, and we give them a monthly stipend, a monthly salary over the 12-month period. So Ali and everybody on the call here, if you have talented students that meet those requirements and their criteria, I highly encourage you to apply and join our program either for a master's degree or for a doctorate degree. Again, who are our sponsors? They spread from local agencies, state DOTs, National Cooperative Highway Research Program, the Federal Highway Administrations, the Federal Aviation Administration, the U.S. Army Corps of Engineering, and so on. So we have really a broad range of sponsors that we work with them basically to advance the sustainability in asphalt pavement technologies. With that quick introductions, I'm going to basically now take you into my technical presentations. This is kind of the short outline what I would like to cover. I would like to start by defining what is thermal cracking, because there is a little bit of misunderstanding about thermal cracking, and we always think every time we talk about thermal cracking, it happens only when there is cold temperature or very low temperatures. And I'm going to show you a little bit that is not the case, right? It's all relative to the material that is being used and in the environment in which that material is being used. And then I'm going to give you a little bit of background about what is that UTSST test, and then show you some of the correlation with the field pavement performance from two independent experiments, one in Minnesota at the Minroad test track, and another one in an actual field project here in Nevada. It's actually about 20 minutes from where university is. And then I'm going to basically close with some final remarks. So let's start a little bit with the introductions about thermal cracking and asphalt concrete pavement. So first of all, I need you to realize that when we talk about thermal cracking, there are two major factors that would influence the presence of thermal cracks in your pavement. One is the climatic conditions. So definitely it's about your climate. It's not only about the how low or how hot it is, but also those daily temperature changes and the rate of changes when you go from low temperature to high, that what is that warming rate and cooling rate. Why this is important? Because if you're familiar with the super pave performance grade system, right, it is based on a 6 degrees C increments. What does that mean? Why it was based on a 6 degrees C? Because if you go from a PG 54 to a PG 60 if you go from a PG 58 to a PG 64, right, what happens to your stiffness? It actually doubles, right? So that's a 6 degrees C increment. So imagine between the daytime and the nighttime, the peaks, you have, over 10 degrees C difference. What's going to happen to the stiffness of your binder? It's going to be more than the double, right? So not only about how low it is, but what is that rate? But also this is all relative to the material that is being used. So you need to use a certain specific binder properties and aggregate properties. And within the binder properties, we want to focus not only on the rheological properties, but also the chemical properties, or what we call the aging properties, and the relationship between rheological and chemical properties. Because you can have a good rheological property, but it may be susceptible to aging, right? So that relationship is very important. And then on the aggregates, also I'm going to show you very good examples here that we have with the data, about the absorption of the aggregate. So if you keep everything the same, right, within two mixes, and you just change the aggregate mineralogy, then there's a likelihood that your cracking resistance is going to change. Now, even though your ingredients, right, your asphalt binder and the aggregates are maybe good quality, but it depends how you put them together. So that's why, we have to test, yes, the raw materials, but at the end of the day, also, we have to test our asphalt mixtures and look very specifically, not only about the fracture properties, but also the viscoelastic and the thermal viscoplastic properties of your asphalt mixtures. So I'm going to give you a ride over here to try to make my point. Okay, this is where we are in Reno, Nevada. Okay, on the map over here, we are at about 4,400 feet. That's the baseline elevations, right? And then the average maximum temperature this is the average, not the peak. It's about 7.6 degrees, right, in January, and it's about 34 degrees in July. Now the average minimum, right, is minus 2.5 degrees C in January, and in July is about 16 degrees. So the difference, if you look at that, right, is about 10 degrees and 17 degrees. So in this case here, we have sub-zero temperature. And we do observe thermal cracks in our pavements. And a lot of time what we observe that those thermal cracks are more prominent when we have highly absorptive aggregates. If we don't account for that during our mix design, right, that tends to dry the mix in the field with time and results with high oxidation and then cracking. So this is a high elevation, low environment. If we drive now south east to Bishop, California. So we moved from Nevada to Bishop, California. Here, actually, if you look at the environment, the elevation is pretty much similar, right, or a little bit lower than Reno, but the extremes are different, right? So here, if you look at that, here we had 10. If I go back, it was 10 and 17. Now we have 17 and 23 degrees. And then again, we have sub-zero temperatures. So now we have more swings. And then also, this is an example. This is Professor Apps. If you know Dr. John Apps, that's him. He's a tall guy. Probably he's a size 11 for his feet. And look at those thermal cracks. They're bigger than his feet. Okay? Now, these two examples are just illustrating the effect of the difference in fluctuation of your or range of temperatures. But what about if we continue driving now south and we go all the way to Arizona, to Tucson, Arizona? So Arizona is a hot environment, especially in Tucson now. If you look, even in January, right, it's the 18 degrees C and there's no sub-zero temperature. And in July are very high temperatures, okay? But still your swings are even, especially in the winter time, higher than Reno. On average, in Reno was 10 degrees C. In Tucson, Arizona, even though it's a hotter environment, but we're at 15 degrees C. Before that, we're about 17 degrees C in Bishop. So this is pretty much similar to Bishop. So now what do you see? You may think, oh, there's no sub-zero temperature. I'm not going to see thermal crack. No, you're going to see thermal crack. Why? The environment is much hotter. So now it's not only about my rheological property, but my oxidation kinetics are going to kick in, and I'm going to have a higher oxidation rate. So my pavement or my asphalt binder is going to age at a faster rate compared to Reno or Bishop. And then because of those swings in temperature and everything, then I'm going to end up, based on the binder that I'm using, with thermal crack. So even with the warmer environment, and this is a good example over here from an actual field project, those are thermal cracks. They're not reflective crack from an overlay or anything, just thermal crack in your pavement. So that's why I like to call it thermal crack and not low temperature crack. And then one more point I want to make at the end is this is a simulation. We took the same binder, asphalt binder, we run the rheological properties and the kinetic properties, and we have a model with a software that allow us basically to predict the oxidation rate within my asphalt pavements. So, and for a given temperature profile or climatic conditions. So we ran that simulation for the same binder at 3 different climates: the Reno climate, the Phoenix climate, which is hot, and the Montana, the Glasgow climate. So what you're seeing over here are the temperature over the year. Okay, so basically the Montana one, which is green, definitely is the coldest, right? We see in minus 10, minus 13, 14 degrees Celsius. Then comes Reno, Nevada. Then comes Phoenix, which is a hotter environment. All right. Now, if I take that same binder and I do my simulation under those 3 different climates, what do we see? what you're seeing over here is the carbonyl area, the carbonyl, which is a measure of the oxidations in your asphalt binder. Remember, the same asphalt binder, I put it in my asphalt mixtures in that pavement, but I subjected it to 3 different climates. What you see is the Reno and the Montana one, they see very similar aging, whereas the one in Phoenix, though we didn't see low temperatures, right, sub-zero temperature, but it oxidized at a much faster rate. So there is a lot of tendency here with that PG64 minus 22. If I use it in Phoenix, Arizona, it's gonna crack due to thermals because it's oxidating at a faster rate. It's gonna become brittle. So I hope I made my point with the thermal cracking, because next I'm gonna start talking now about the test itself, the UTSST, the Uniaxial Thermal Stress and Strain Test. So if you are familiar with the TSRST, the Thermal Stress Restraint Specimen Test, which was developed as part of the Strategic Highway Research Program, well, basically the UTSST is basically a version from that. It stems from the TSRST. It's a very good test, but it uses beam, the TSRST uses beams, prismatic specimens, and it does only, or it looks only at the fracture temperature and the fracture stress. The problem with that test is the repeatability, because you have the edge effect, it's a beam, and we were not getting a good repeatability, especially in the stress buildup. So what we end up doing is to improve the testing repeatability is to use cylindrical specimens. And also we made some additional improvements to the platens and so on, but also we were interested to measure during the test also the thermal strain for an unrestrained specimen. So what we end up with is basically now what you see here. We were one of the first, if not the first, to take a gyratory specimen and core it sideways, like what you see over here, and make a cylindrical specimen out of it. And then we glue the 2 top and bottom platens, and we put it in a chamber. And then in that chamber, we have a closed feedback loop where while we're dropping the temperature at a constant rate, we maintain the height of the specimen constant. So what does that mean? Imagine that the specimen is free to move. When you drop the temperature, what's going to happen? It's going to shrink, and you're going to end up with some compressive thermal stresses. But now what we're doing, we're saying, nope, we're not going to let you move. We're going to restrain the movement. By restraining the movement, what's going to happen? You're going to end up with the opposite effect, and you're going to end up with thermal stress in the specimen. So you're going to see that thermal stress build up until a point where the specimen is going to give up and it will fracture. Now, at the same time, you see here at the bottom, this is the unrestrained specimen that we put it over here. We lay it down on rollers and we measure with LVDTs how much is shrinking. So if you think about it now, we have a thermal stress build up and we have a thermal strain. From the thermal strain, we can get the coefficient of thermal contractions. And now if we combine the thermal stress and strain together, we can calculate a modulus. And that's the whole idea of that basically test. This is a very typical results where you see the red is the stress buildup with the temperature drop, and the blue is basically the strain, your thermal strain, with the decrease in temperatures. Okay, now also an additional change that we made is the original test start at 5 degrees C. Now we start at a much way warmer temperature at 20 degrees C. And the reason for that, because we want to characterize the different phases of the asphalt mixtures. I want to characterize when the mix goes into the viscous softening, to the glassy, viscous glassy, to glassy hardening, to the crack initiation, all the way to fracture. This is not new. It's coming from the basically rubber and the polymer science and analysis. We adopted that for our asphalt mixtures, trying to identify those different zones. So I'm not only interested when my mix fracture, I want to know at those different phases how it is behaving. And I want to characterize that and use that in my analysis. So we have the stress, we have the strain, we do calculations. right? And mathematically, we come up with a modulus. We call it the thermal modulus as a function of temperatures. And when we look at the curvature of that modulus, we identify those different zones that I talked about. And you're going to notice that the modulus is going to reach a peak, and then it drops. Okay? Now, that peak would prove this is the crack initiations. So in this test, there is no notch in the specimen, right? So it's a continuum. But then as you're dropping, the cracks are gonna forming in. And what we proved that this is the range when you start seeing the crack initiation, and then they propagate until it fractures. Now, this is a good example where you see a difference between a crack initiation and a fracture. So this one started to crack at around minus 18 C, but it did not fracture at till about minus 28. And that difference in the temperature between the two, between the initiation and the fracture, that's what we call the delta T UTSST. All right? Don't get that confused with the delta T from the binder, right? Delta TC from the binder. This is from the mix. This is testing basically the asphalt mixtures. Now, why this for us is important? Because what we saw with some mixtures that are brittle, that delta T is very, very small, or even sometimes is 0. So when you're dealing with a high wrap, RAS mixtures, reclaimed asphalt shingles and everything, they may have a very high modulus. They're very stiff, but they don't have tolerance. They don't have any strain tolerance. The minute the crack initiates, it fractures. So that is telling us a lot about the mixture behavior. And this is where basically we can take this and translate it in the thermal stress curve, and we can see at what temperature, what stress, and same at what strain level also that occurred. Now, while those different zones are good and everything to look at them, but also we want an overall index that allows me to compare mixtures, just to make it more simplified. So we go back now the next phase, after we identify different zones, we plot the stress versus strain, and then based on the area above that curve and those different zones that we identified, we calculate what we call the crack resistance index. So it's an index that takes into consideration the viscous softening, the glassy hardening, the crack initiations, and the fractures, right? We take all of these and the interaction between them into consideration, because some may have large resistance, right? But then once they crack, they fracture, where some others may not have a large stiffness or large resistance, but they get to a point, they initiate by having strain tolerance. It takes time to fracture later on. But that's not the end of the story. Why? Because if you give me a mix and I measure the cry, I can tell you what that cry, cracking resistance index. But I cannot tell you if this mix is good to use in location A or location B, or in Reno or in Vegas, or in your location. So we need some kind of a climate adjustment factors. And what is that environmental factors? Is basically now we go back and we compare the strain when the specimen was fractured to what we call a critical strain that's coming from my environmental conditions. So from your climate conditions, from your PG grading, you have a low temperature grade that you want to meet, that we translate that into a critical strain. Now, if your fracture temperature is exceeding your critical strain, your climate factor is going to be greater than 1. If your fracture strain is less than your critical strain, then your factor is going to be less than 1. So now I'm adjusting the mix property based on where I'm going to be using that mix, based on the climate where I'm going to be using that mix. And then a lot of study that we've done prove that the test is sensitive to aging level, and we have tons of data on that. It's sensitive to the aggregate mineralogy, different air void level, polymer modifications, asphalt binder content, the type and the amount of recycled materials. So the test was proven to be sensitive to this, which is very important to us because we want to make sure that my test can capture changes in the mix compositions and mix properties. With that being said, now I'm gonna show you what is the relationship or validation, if you want, of that test. Because this is all good, and in the lab, okay, I can capture all of this, but does it correlate to the field? Do I see some good correlations with my UTSST test results? So I have two separate experiments over here. The first one is from the Min-Road experiments. Min-Road is really a test track. It is, if you're familiar with the state of Minnesota, north of the United States, Min-Road is basically northwest of Minneapolis. It's about an hour and a half or so from Minneapolis. Back in 2015, they had a partnership with the National Center for Asphalt Technologies and built test sections. And those is basically the experiment objective was they called the Min-Road cracking group. It's really to evaluate different cracking tests and then relate those cracking into their field performance. As far as the climate, you know, the temperatures, it can be in the low -28 and the -30s and so on. Just to give you, it's a much colder environment because it is really the borderline. What you see here on the top is really Canada, right? So it's really north of the United States. So we had those cells, right? The test sections. They had a varying levels of thermal cracking resistant mix designs, and I'm going to show you what are basically those different 8 different mixtures that you see them over here. I try to highlight them just to help you understand them. So what are these? There's 8 mixtures. The top 2, so all of them had some sort of recycling material. All of them had RAP. RAP is reclaimed asphalt pavement with the different proportions. Only the first 2 had RAS, recycled asphalt shingle, at a 5%. So if you look at the first 2 mixes, they have the same binder, the same RAS content, but 2 different RAP content, a 20 and a 10%. And you can see the asphalt binder ratio. This is, 40% of the asphalt binder in the mix is coming from the reclaimed materials. And this one is about 27%. Then the next 2 mixes over here, there's no RAS anymore in any of the other mixes. But these mixtures maintain the 20%, the same binder grade, but now we have a different end design, right? So selecting your asphalt binder content at a different end design, different air void levels. And then the cell number 20 is actually bumping up the RAP to 30% and softening the binder. So going from a 6422 to a 52 -34. Now, to be honest, the -34 is basically what is more appropriate for that location. Their binder grade is -28. And if using RAP, you need to soften it at least 1 grade, that would be -34. The reason they use here 6422 is to create different ranges of thermal crack, right? Different combinations, because they wanted them to crack in the field so they can validate the lab test. If all of them, turns out to be good mixes, so how you want to know if that test is telling you what's good from bad? Then cell 21 and 22, it's now not a 5234, it's a 5834. But then the difference between those 2 is everything is exactly the same, but the aggregate type is different. Here they're using limestone. So 2 same mixtures, but swapping aggregates and changing from one aggregate type to another. And the last one is dropping the RAP amount and then using a high polymer modified asphalt binder, which is 6434, right? So this is just a little bit the combination. So all of them has RAP, some has RAS, some has only PG6422, and then you have a PG5234, PG5834, and PG6434, and different combinations of RAP contents, and then also with one of the cases, different aggregate mineralogy. So the experimental plan is large. I'm not going to go through all of it, and we didn't cover all of it, So on the left-hand side, the distress data that came from the Min-Road, and I really have to acknowledge, everybody at Min-Road They were very helpful in providing the data, sampling, shipping us materials, sharing a lot of information with us. That was really very, very collaborative and very helpful and useful for us. And then on the right-hand side is basically the lab data. So we're going to have field data on the left-hand side, and we're going to have the lab data. Our university did the UTSST testing, and then University of Minnesota did the mixed BBR and the semicircular bend test at the low temperatures. The mixed BBR is similar. Those are slivers like the BBR that you do on the asphalt binder, but this one you do it basically on mixtures at low temperatures. So if you look, again, this is our results. I don't expect you to grasp everything. Just want you to focus on the bigger pictures. So starting in the top, what you're seeing, those different error bars, those are the temperatures for those different mixtures when we identify the glassy region, crack initiation, fracture, and the delta T, which is the difference between initiation and fractures. What I want you to look at generally that there's a variation, right? We see some changes, and then also we see that how there's a change between the crack initiation and the fracture that's experienced with that delta T, that yellow line over here, right? So if you see that delta T large, that means when there's initiation, it took some time before it fractured. When you see it, for example, here closer to 1 or 1.5 degrees C, this is telling you that once it basically, the crack initiated, it almost fractured right away, right? Or within a degree or so. And then here at the bottom is the CRIEnv. This is basically our index. This is the beauty of the index. It allows you to lump everything together and just look at one numbers. So again, you see those two. This is where we had the RAS. It didn't matter if we basically change the amount of the RAP because the RAS was overcoming or is controlling the behavior. These two is when we change the number of gyration of the design air volts. Okay, this one over here, we'll start using a softer binder grade. That one specifically over here is the one that has a PG 52 minus 34, which actually showed that when it was short-term age, very good relationship. But when we long-term age it, that's what the orange bar is, it actually dropped. So there's something into it. So it might be good early on, but it might be susceptible to aging. The one that's showing relatively higher values is basically cell 21, which is a 5834 with only 20% RAP. Whether it's after short-term and long-term, it's showing really the best performance, especially after long-term. Look at this. When we change the aggregate type to limestone, everything the same, just the aggregate type, it drops significantly. All right. So don't take the assumption that the aggregates are not important. They're significantly important. Why? Because their absorption might be different, right? The film thickness might be different and all of that. And then the high polymer actually did not perform as expected in this study. And I don't want to, generalize this because there was some challenges here with the high polymer that was used. Okay, very good. Now you may think, well, this is great. How does it correlate to the field performance? Before we get there, I want to show you also the correlation of the UTSST test with the mixed BBR and the SCB. The mixed BBR, it's more about, if you want, stiffness and strain tolerance. The SCB, it is more fracture and about toughness. And why I like this, so the color is basically telling you about that Pearson linear correlation between the different parameters. And the reason I like to bring it because I want to, emphasize that the test, especially the CRIEnv, it has a good correlation with both the SCB and the mixed BBR, right? Depending on the parameter you are looking at it, that UTSST test, it means to me, it is capturing the initiation and then the propagation, the tolerance and the toughness and the fractures. So in one test, right, I can get both. That's the beauty of this one. And now again, the question will be, well, how does it correlate to the field performance? Well, here you go. This is a field performance. So this all was built back in 2016. We got our samples, and then we tested them around 2017, right? So we got all the results, whatever now, 5, 6 years ago, and now we're waiting for the field performance. The first 3 years, there were no cracking. After 3 years, for all of them but one, which is cell number 20, they start seeing cracking, okay? Interestingly enough, the one with the limestone, the crack was propagating fast. Once it started, it propagated very fast, where the other ones was more like a slow propagation. So the first point I want to make here, because if we look at the 3.5 years and we try to compare the mixes, you can see over a year how the mixes ranks. But then if we look at them after 4.5 years, so a year later, the ranking changed. So a very important lesson is that you need to know when to compare your lab data to the field data. And most importantly, you need to match them, because in the lab, you're doing some sort of an aging, right? You want to match that aging with what's happening in the field. If you compare them early on that the mix hasn't aged enough, you're not going to see a good correlation. If you compare them here, even though some of them are cracked, but if that aging level doesn't match your aging in the lab, you're not going to see good correlations, right? So this is important to match them together. So now we looked at that correlations between the UTSST parameters and the cracking that we're seeing in the field. And we saw several of the parameters have a very strong correlation, very high correlation, right? This is very, very promising to us. Now, you may say, oh, your CRIE is barely moderate, it's borderline. Well, I'll tell you why, and I'll show you why. It's still the correlation is very good, and I'll show you why. But look at this, the fracture stress, not at all. And that TSRST, the early days of the TSRST was all based on fracture stress. But now when we look at the initiation, the delta T, the CRIE, we have a very good correlations. And I'm going to focus on that. I'm going to show you that. Look at this. This is here on the left-hand side, the CRIE. Look at this. This is the cracking. It's beautiful. The higher the CRIE, the better. And that's what we're seeing. So the reason your correlation is only 0.59, because we have a lump over here of mixes. So those still, they're all performing very, very similar. So they have a very similar cracking, and they're ending up with a very similar crack resistance index. That's why the correlation is not coming, very significant. But there is really a very good correlation. Now you look at the T initiation, very strong correlation. You look at the glassy temperature, very strong correlation. You look at the delta T, very good correlation as well, right? So the test is correlating beautifully, actually, with the field performance data if we compare it at the proper time, and it's capturing those different changes in the mixes. Now, I wish that we had beyond 4.5 years, but they had to replace, all those for a new experiment. I wish we had more, because I anticipate, based on the data we had, because of the long-term aging, that 20 is going to do very well, but once it cracks, it's going to propagate fast, like the orange one. But unfortunately, we didn't have enough field data. Very good. Now, quickly, to go through the next one, and I'm getting toward the end over here. This is a totally separate experiment. This is from the NCHRP 9-58 projects, where we had multiple test sections within the states. One of them is in Nevada, where we ended up using different sections with different wrap contents and different rejuvenators or recycling agents. This is basically the map where we had those different sections. They were all constructed anywhere between 2014 and 2016. The Minnesota one, this is pretty old. That was before that experiment, what we included in here. But these are basically the one I'm going to focus on is here, the one in Nevada. All right. So that was constructed back in 2015. We did our testing, and then we've been monitoring the performance. We didn't see any cracking until this last season, after that harsh winter that we had last year. I don't know if you know, but we experienced 250% of our average in terms of snow. It was extremely harsh winter. It kept on snowing every other week, nonstop. We got a lot of snow. It helped. It cracked the pavements. That will help us to validate our experiments. So what are the different mixes that were used on the same stretch? It's the same stretch in the actual field projects where we had a mix with no recycling, no wrap. That's what we call the virgin mix. We didn't change the binder grade because the state over here and the agency mandate the use of a 6428 polymer modified binder. So the binder remained the same. The next one is what the state typically has been using, which is 15% wrap, no change. Currently, this is the standard. And then we said, let's use 30% wrap, which ended up being an ABR or reclaimed binder ratio of 33, but with no recycling agent. And then the other two experiment is with two different type of recycling agents, the tall oil and the aromatics. Here is the data for lab mixes after short-term aging and long-term aging. And here's the data for plant-produced mixtures, the reheated plant-produced mixtures and after long-term aging. If you look at both, there's a consistency. They go down and go up because you have the virgin, 15% wrap, 30% no recycling, 33% with the tall oil, and 33% with the aromatics. Now, the aim was to use the recycling agents that we allow us to bring it back to the control, which is the 15%. Okay, we were only successful with the A2, but not with the T2 with the dose that was used, because at that time, the dose was recommended by the supplier. Now we have a process where we go and we evaluate. So more likely here, we needed more than 2% to bring it up. And again, 2024, we got field performance data, right? And then guess what? They rank very, very nicely with the field data. This is the virgin one. Still haven't seen any cracking. These two over here, this is the A2 aromatic with the 30%. And then the next one is basically the control with the 15%. Pretty much like what the lab is telling us. And this is basically with the tall oil, and this is no recycling agents at all. Again, you have a beautiful correlations that is consistent with what we've seen on the mineral. So to wrap up, to close, we believe that the UTSST was able to capture not only the fracture, but also the relaxation and propagation of the asphalt mixtures. It's a very promising test. It correlated very well with feed pavement performance, but a key aspect to keep in mind, not only with the UTSST, with any test that you're trying to correlate with the field, is that laboratory aging condition needs to match that field aging conditions. Okay, keep that in mind. And also keep in mind that the ranking of your mixtures in the field can flip depending at what time, right, you're looking at the field pavement performance. Now, UTSST is not a test that you can use on a daily basis, and we acknowledge that, right? It's more involved, but we believe it's a very good test to evaluate new materials, additives, and allows you to study the impact of the thermal cracking resistance of asphalt mixtures. Some references for you, and I really appreciate, sticking around and then listening to me for 40 minutes or so, and I'll turn it back to Elie for any questions.
Well, thank you so much, Professor Hajj, really for your interesting and thorough the speech. It was really insightful and providing really new insight into the thermal cracking resistance of asphalt mixture is it shows that how really your team and what you've done over the past years on this research is really how it's evolved. And really thank you so much really for your the information that you share with us. Okay, so I think we can. It's now time to start the Q&A session. If among our audience anyone has any question, please, whether you raise your hand and turn on your mic or type your question in the chat box. Yes, Rama, please, yes, turn on your mic and ask your question.
Hello, could you hear my voice?
Yes, we can hear you.
Okay, thank you, Dr. Elie dan Dr. Ali. Yeah, I'm Rama from Indonesia. Sorry, I came late because I guess most of half of the presentation I just came. So I wonder about because you earlier you mentioned and explained about the field testings. So you sprayed the asphalt right to the field and oversaw the performance of the surface. I wonder if you applied some maybe you can give us a recommendation if a cracking happens, what should we do during the field test? I mean, because in your case there is no cracking, right? But if later if you want to make a field test and something happen cracking, should we treat them or should we just leave it?
So if you're talking about more monitoring, right? With time,
yes.
When you start monitoring the cracks. So if the cracks start occurring, typically if they are the crack width is still small, less than 1/4 of an inch, typically you do nothing. When you start growing beyond 1/4 of an inch, typically what we would recommend is a crack sealing. So if those experiments, you want them to last longer so you can monitor them and then validate your lab data, my recommendation will be to basically, once they become wider cracks, right, start sealing those cracks and then continue to monitor those and then documenting these, because you don't want the, well, for example, the one in Nevada, we were hoping that the agency won't come in and then do any slurry seal or a chip seal to cover the cracks, right, and try to slow down the oxidation, because we don't want to interfere with the study. We wanted them to keep it exposed, age, and then if they have any cracks, we're okay if they seal them. And we recommend them to seal because we don't want them to infiltrate and start having some other problem, moisture damage problem. It's the other way around. We want them to seal, and then we'll keep monitoring with time.
Okay, thank you, Professor Hajj, and thank you, Ramo, for your question. Okay, our next question is from Haibo. Yeah, Haibo, please.
Hello, Professor Hajj. Hello, Elie, can you hear me?
Yes, we can hear you.
Okay, Professor Hajj. I have two very simple questions. Like, we know some aging will affect the thermal cracking of our asphalt pavement. So because there are different types of aging, in your study, have you considered the physical hardening and UV aging in your research?
So this, no, the short answers to this one specifically, no, we did not. We went by a protocol of aging the asphalt mixtures itself. Now, okay, we do have another study for actually two bright PhD students that completed their work at UNR that looked into the kinetics, but in the oven, under oven aging at multiple temperatures. So they've done different durations, some of them for really months, right, 9 months and beyond, and different temperatures for the binder, the mix, and the binder in the mix. All right, and we looked at the kinetics, where we looked at the rheological properties versus the carbonyls and other chemical properties, but not the UV lights. It's the regular oven aging type of experiments.
Yeah. Regarding for like physical hardening, because I know in Canada they have many standard on like
Physical, yes.
physical hardening, like asphalt to TP 122, like to select the asphalt resistant to physical hardening. So in mixture, I don't know if like UT your developer the test can simulate it as the physical hardening. Maybe we can condition the sample for a long time, or maybe we can change in the like cooling rates to simulate it.
We did very limited in terms of cooling rates. We did very limited experiments by changing. Very good question, by the way. Changing the cooling rate, and also we did the very limited testing by, instead of taking the cooling all the way till fracture, we take it into before the crack initiations, right? And then we warm it up, and then we cool it, and then we warm it like a cycling, if you want, right? Again, but those takes time, and we did not, dive into too much into it. But the equipment itself will allow you that, because you can put the samples in the chamber and then maintain the temperature constant, and then you can drop it. Even we did some experiment. We started with a given rate, and then we changed the rate, because we did analyses on the actual thermocouples, and we saw what would be the warming rate and the cooling rate. And what we find out on the cooling rate, it's a bi-cooling rate. It drops fast and at a slower rate. So we simulate that cycle. We simulated that cycles in our equipment. But again, those are research, right? Not really something practical to be able to use on every day. But the equipment has that capability. It allows you to do that.
Okay, thank you very much, Professor Hajj.
Okay, thank you, Haibo, for your question, and thank you again for Professor Hajj. Okay, next one, question from Abdullah. Yes, Abdullah, please turn on your mic and ask your question.
Okay, thank you, Dr. Ali, and thank you, Professor Elie Hajj, for your nice presentation. I attend more webinar presented by Professor Elie Hajj through his department, the name DABT or DABT. Yes, I attend more webinar. Last webinar about balance mix. And here in this presentation, you talk about super beef. I need talk us about the consideration of thermal crack in balance mix design. This is the first question. And first thing make my attention, the shape of the cylinder. I thinking the thermal crack, like stiffness test or like that, and all stiffness test, the specimen as beam, BBR and stiffness of concrete, all shape of sample is beam. Why here the shape of sample is cylindrical, like when we need to test rutting or like that? This is the first part. Huh? And after you reply and ask again.
All right, so first on the balance mix design, I guess the question is, so right now the balance mix design, the focus is to balance really multiple mode of distresses. One of them being typically the rotting or permanent deformation, and then the other one is cracking. But cracking, it depends on the locations. Intermediate cracking might be enough, but in some other location, like if you go to Minnesota, North Dakota, South Dakota, they need, beyond just intermediate cracking, they also need like a thermal cracking test. So because for the same reason of what we derive over here is that, the behavior of the material is going to change when it's at the warmer temperature versus the, cooler temperature. That's the whole idea of going from 20 degrees C down to sub-zero temperature to capture that behavior, that phase change in the mixtures. So with the balanced mix design, I agree with what you said. The focus been really on the intermediate temperature, but there are states now where they know they have a thermal cracking problem. They're also looking at what is that test. The challenge is we don't have a simple test, right? The closest one is basically the SCB at a low temperature. But for the agency, that's still a little bit challenging because you have to do a notch, right? And cut your specimens and so on. So it's not, doesn't have a quick turnaround to be used during production and so on. So this is where if you want, the main challenge is we don't have really a very simple test. Now, going back to your questions, the second one is about the cylinders. Well, yes, the cylinders are typically used for compressions, right? And it's very good. Why? Because it eliminates the edge effect. And that's actually where we got the idea from, is with the prismatic, with the beams, we're getting a lot of edge effect and the variability is very large. So why don't we use cylinders? Now, a lot of time when you do tensions, in the past, they've used cylinders or they use those duck bone type of shape. Why you want to be like the ductility test, right? On the binders,
Yes.
which unfortunately we don't use it anymore. But it's really, you try to create a thin sections so that you specify where you want it to crack. So here there are some study where they looked at the duck bone in the mix. But again, our challenge was, well, if we're going to add a duck bone, then that's going to add to the challenge, how to make the specimens and everything is going to become even more complicated. So we wanted to go with cylinders for two main reasons. One, in the lab, we do the gyratory cylinders. In the field, we get cores. Second, we wanted to take the core sideways because then if you have a thin lift, you can still take a sample out of it. Plus, it is perpendicular to the direction of the compaction and how the mix is going to contract and expand. So we preserve the orientation of the mixes. So while keeping that in mind, the challenge was to find the right specimen size. So that's why we looked at the geometry, we looked at the nominal maximum aggregate size, and based on some studies out of Texas A&M, we looked at what would be a representative volume element, and that we used as a minimum that we came up with that 2.5, like 5 1/4 inch as the specimen dimensions.
Okay. So the second part of my question related to the structural pavement. I use Ashware software and make some trial for some type of thickness of pavement. Unfortunately, first I'm here in Saudi Arabia. Unfortunately, every trial I get failure in thermal crack. The software need threshold input, routing inputs, fatigue cracking, top down, and thermal crack. The thermal crack failed in first 2 years, but the routing stay for 10 year, 20 year. I need some suggestion to solve this structurally. And
well, I need to caution you because are you using the nationally calibrated model?
Use what?
Are you using the globally calibrated models that are built into the software?
Yes.
Yeah, so that's the first, problem is that you shouldn't be using those globally calibrated models unless you prove that they are applicable locally. I'm not sure about the type of material that you're using there, but I can tell you we went through the process and we recalibrated the models for Nevada, even the rotting models, the overlay reflective cracking models, the fatigue, the cracking models, everything we had to recalibrate because the material that we use was not part of the mixtures that were used to come up with the globally calibrated models. So I really caution you to just take the software and run the analysis and then rely on the results. It's good to see where, what does it give you and what so on, but it's likely that it's not going to be applicable to your case. And unfortunately, you have to go through a calibration process. And I'm happy to discuss with you, how we did it and all of that. But it's going to require really some testing. It's going to require field data, performance data, and then going through the calibration process. There is a very good ASTO guidelines on the calibration process and so on. That might be a very good starting point.
Okay, thank you. Last one, increase or decrease the thickness effect and on thermal cracking? Thickness of the asphalt layer.
Yeah, good, very good question. My answer would be it depends, because some thermal cracks or some modeling we've seen that some really thermal cracks may start at the bottom of the AC layer. And that's when you have a large difference in the stiffness between the AC and the underlying layer. So while the majority, or we anticipate that the thermal crack will start at the top, but there are cases where your thermal induced stresses can be much higher at the bottom of the AC layer because of that friction and the difference in the coefficient of thermal contractions. For that case, then your thickness is going to play a role. Now, if you're trying to tie that back to the pavement ME, in the pavement ME, there are also some drawbacks, because the thermal cracking in the pavement ME, okay, once it looks at the thermal stress and compared to the strengths, and there are limitations in the way that it doesn't assume the variation in strengths with aging, and so it's a constant value. And then once it reached that strength, or once the likelihood and it cracks, the software, though it has a Paris law for propagation, it doesn't capture that very properly, and then it only takes one cycle to crack throughout the entire depth. So what they end up doing is really divide that into 4 layers, so, or let's call it sub-layers. That way it takes 4 cycles to crack the entire layer, which means, let's say, 4 years. But then guess what? Based on the probability and everything and the amount of cracking on the surface, you can only reach 50% of the depth. And that's what explains your 2 years over here.
Okay, thank you. And finally, I see your department and your staff, and you say you have capacity to take PhD student. And I know Nevada, and I know some graduate student from your under your supervision, like Nimeri, Sudanese one. And every time I discuss him to make recommendation for me to do Professor Elie Hajj, but I think he is not found time. Today, through Ali Rahman, I hope I found chance to take my PhD in Nevada, Reno.
Well, let's communicate on the side. Email me and let's talk. See what do you have a master degree? You don't have? I mean, we can talk about it, and then I can share with you our programs, our requirements, and all of that. So we can definitely follow on the side. Yes, absolutely.
Okay, thank you, and thank you, Ali.
Yeah, thank you. My pleasure. Okay, thank you. Thank you so much, Professor Hajj, again, really, for your time, very carefully answering all questions and patiently. And thank you to all audience for their participation in QA and session. I think with that, we can wrap up our today presentation. So again, I appreciate Professor Hajj for his time. So do you have any closing remarks, Professor Hajj?
I think that was a great discussions. I enjoyed those discussions. I'm glad that you guys are still fresh in the morning and then willing to listen to asphalt and all of that. And I hope I can visit one day in person. But thank you very much for reaching out and giving me the opportunity to talk to you all. And please feel free to reach out. I think you have my contact information, everything, right? If you have any questions, or I can point you to the right person or the documentations that you can basically make use of it. Again, thank you very much.
Sure, our pleasure, my pleasure. Really, thank you. We are also looking forward to hopefully expand this collaboration, and hopefully we could this one day even see you in Chengdu, have you in Chengdu, or discussing about the further collaboration in exchange and academic and research and etc. Okay, with that, I think we are already running out of the time. Thank you so much, everyone. Thank you, Professor Hajj. Thank you to all audience, and please stay tuned for our upcoming webinars. Next week, we will have 2 other webinars with 2 experts, and I will announce in advance. Thank you, everyone, and have a nice day. Thank you, Professor. Thank you, everyone.
Thank you.
Bye-bye.
Bye-bye.
Bye.